This is G4, diffraction grating. And so what does diffraction grating mean? Well, we've looked at single slit, we've looked at double slit. However, when you have many slits, like 100 for every centimeter or millimeter, it's called a diffraction grating. So you basically are shining it through many slits at once. And this picture, we'll see later on, this is an experimental picture, is when you take white light and shine it through the diffraction grating, whatever. A lot of times they'll be written, 400 lines per millimeter. Okay, so to find how the slit width, you would do 1 divided by that number to find the opening of just 1. And so here you notice a different intensity pattern, or diffraction pattern actually. The central maximum is actually white, and then your subsidiary maximums are the Roy G. Bibbs, and so they've separated because of the angle into their colors. And you'll notice that the first order, n equals 1, those are of greater intensity than your n equals 2s. Okay, so just keep that in mind. We'll see it again in the next slides. So, why do we increase the number of slits? Well, there are several reasons. Increasing the number of slits increases the sharpness, the clarity of the fringes. A lot of times, whenever you just have 1 or 2 or 3, they're a little blurry. And so we add more just for the clarity. The maxima maintain the same separation. And so the X, this is the X value of your fringes. Okay, they remain the same. So changing the number of slits doesn't change that. As long as the wavelength and the screen length and the slit separation are all the same, then that's true. And then it also increases the intensity of the central maximum. And so you get that drastic change. Alright, so the diffraction grating is parallel, equidistant, closely spaced slits that can transmit light. In practice, lines are ruled onto glass with a diamond, leaving a transparent glass in between. So, they're cut very precisely. So here's what you would do is shine the light, white light, through both coarse, which means 100 lines per milliliter, to fine, 500 lines per millimeter. Now, if I have more lines, that means they have a smaller opening. And so you can repeat placing red or green filters in front of the grating so that you can observe the different fringes. Now we don't have the capabilities to do this, but again, the experimental picture would be something like this if you had the white light without the filters. But you would see the same effect. All the filters would do, if I filtered through a yellow filter, then you would only see the yellow fringes. But you'd still see the same spacing, the same intensities, and changing the filters changes which color you're seeing. Okay, so for the 0th order, that's in the center, we saw white light. For the first order is where we saw the bright bands of your colors, and then your second bands were the second orders. And they were identical, except they were a little less intense. And violets are nearest to the center, red spreads out the furthest. The finer grating, in other words, more lines per milliliter, form less orders and further apart than on a coarse grating. So this is just, things to maybe keep in mind there. So here's some of the geometry. We've got many openings. Here's just 3. Monochromatic light, and we'll assume it's already coherent. Passes through. We look at one set of parallel rays, and it says that the light is diffracted at 0 degrees to the normal, and those triangles are going to lead us to this equation. And so the d sine theta goes back to this picture and this triangle. Okay, you're in lambda here, and it was AN, I think. AB, let's go back, sorry. Yeah, AN corresponds to your n lambda, which is your path difference, which then corresponds to the d sine theta. So of our triangle, let me try and remember it. We had A, we had n. This is your n lambda. Here's your d. There's your theta. So sine theta, it would be equal to the n lambda over the d. Solve for it, and you get this equation. This is on the data booklet. And n would be what order of the fringe it is. And light from all slits that constructively interfere would be the bright regions. And so here's some questions for you to consider, and I think that takes care of the video, so you can go back to the PowerPoint and look at these. Oh, last reminder, on the data booklet you'll see 5 equations, but it really only boils down to 3 because they actually duplicate. I don't get it, but they're these 3 basic equations. The one without the angle, and this one is for constructive interference for the bright spots. And if it's a path difference for a dark fringe, you have that +1/2 factor. So this is for your dark destructive interference, okay? And then the one with the angle, that would, you know, if the problem involves an angle, you're probably using this one. The 2 on the left are actually duplicated. They just solve for a different variable, but really it's just these 3 equations.